right, our last video before we summarize Le Chatelier is Le Chatelier's principle, or like that video said, Châtelier's or something like that. But the effect of volume or pressure changes on a system as well as catalyst because it's super short. So the key thing is that anytime we're talking about volume or pressure, we have to make sure we're only looking at reactions that have gases. You cannot compress a solid. You cannot expand a solid. You can't do that with liquids either. The only species that can be compressed and expanded are gases. Now, just a principle is that to understand what pressure means, to me, when I think of pressure, it's the number of times that the molecules inside a container will hit the sides of the container. So if you look at something that has a high volume, it will have a low pressure. There's lots of space for those molecules inside the container. They're going to hit the sides of the container far less frequently than this scenario where we have a low volume and a high pressure. You have the same number of molecules in a smaller space, so they're going to hit the sides of the molecule more frequently. So this scenario here is a much higher pressure scenario than this place. So we always include volume there because volume is a really good way of changing pressure. So if you increase pressure, that's happened because you've decreased the volume. So if you look at this scenario here, and this is this point up here, the more moles of gas you have in a certain volume, the higher the pressure. If you decrease the volume, right, so you push this guy down, you are going to increase the pressure. You have more moles of gas in a smaller volume. What that's going to do is it's going to increase the concentration of all the gases. So when you think about concentration, if you took the same size rectangle in both of these containers, this second container that has a low volume and high pressure, it has more molecules per whatever size that would be than this one in the higher volume that has lower pressure. So the way that your reaction is going to shift to decrease the pressure is it's going to see if your reaction can combine certain molecules so that you have less molecules present. In other words, you're going to favor the side with less moles of gas versus if you were to increase the volume, which would decrease the pressure inside the container, that would decrease the concentration of the gases. So the reaction will shift to increase the pressure by increasing the concentration. So it will go towards the side with more moles of gas. So if we look at a scenario here, this one I've got sulfur dioxide and oxygen forming sulfur trioxide. This releases heat. If I were to increase the pressure, increasing the pressure by decreasing the volume, the concentration of all species would increase. So equilibrium will shift to decrease the pressure. In this case, I have 3 moles of gas on the left and I have 2 moles of gas on the right. If I'm trying to decrease the pressure, I'm going to shift right towards the side with less moles of gas. If you look at the concentration diagram for this, so everything's coming in and we are at equilibrium. The red is our concentration of sulfur dioxide, the green is our concentration of oxygen, and the blue is our concentration of sulfur trioxide. When we increase the pressure, what you'll notice is there's a spike up for every single species. So versus when you increase concentration, only one species increases. If you increase pressure, the concentration of all species is increased. So then you shift towards the side that has less moles of gas, which is the right. So you're going to have an increase in the concentration of sulfur trioxide, but you're going to have a decrease in the concentration of oxygen and sulfur dioxide. I didn't put that into words, but you can see it in the diagram. You can write it if you want. right? So the concentration of sulfur dioxide and oxygen decreases, the concentration of sulfur trioxide increases to compensate for the shift. If you were to decrease the pressure, the concentration of all species would decrease. So you're going to want to increase the concentration. So equilibrium will shift left towards the side with more moles of gas. If you were to look at a concentration diagram for this, again, all your species, that's coming out of my mouth weird, species, is coming in at equilibrium. So coming in with an equal concentration. And then you're going to have your shift. So you're going to have this thing that happens. Now, when you decrease the pressure, then all the concentrations will decrease. We are then going to shift left towards, now let's label these. So this is SO2, this is O2, and this is SO3. So we are shifting left so that we get more moles of gas. So we are going to have that sudden drop, and then we're going to increase the concentration of SO2. We are going to increase the concentration of O2, and then the concentration of sulfur trioxide will decrease. So you'll have an increase, and a decrease until this new equilibrium is going to be established. All right, so taking away the diagrams and just talking about two different scenarios. First one we'll do together. Actually, that second one's tricky. Why don't you do the first one? So pause the video and give this one a go. So if the total pressure of the system is increased, you've got 1 mole of gas. On the right, you have 3 moles of gas. If you increase pressure, you want to decrease the number of moles of gas. So you are going to shift left. If the total volume is increased, that's going to cause a decrease in pressure, which means that you are going to shift right to increase the moles of gas and increase the pressure of your system. This next one I threw on because it's an interesting concept. So if you look at this one, again, we're going to have the total pressure of the system this time decreased, and then the total volume is going to be decreased, which is going to decrease the pressure. Oh, sorry, increase the pressure. Whew. Decrease volume, increases pressure. Which way will we shift? Well, we always look at moles of gas. When you look at this reaction, you've got 2 moles of gas on the left, 1 plus 1, and then you've also got 2 moles of gas on the right, 1 plus 1. So which way would the equilibrium shift to counteract this change in pressure? Well, it can't. So you would just have a decrease in concentration, and you wouldn't be able to come back to that same equilibrium. So the equilibrium will not shift. Right? There's nothing I can do. I counteract it with a change in moles of gas, and so then I wouldn't shift left or right. All right, so I said this video was also going to include catalysts because it's short. So catalysts, consider the equilibrium system. Let's go back to that N2O4 plus heat goes to NO2. So I've just reversed the reaction, but it doesn't matter. If I add a catalyst, right? So let's say I added a catalyst to the system. What will happen to equilibrium? Well, adding a catalyst decreases the activation energy. It'll speed up both the forward and reverse reactions, so equilibrium is reached faster, but it just stays at equilibrium. So potential energy diagram, remember that the wall the frogs have to jump over is just lower, right? It's a lower activation energy. And all that's going to happen, if you look at the difference between the gray graph versus the red graphs, is that we end up reaching the same equilibrium concentrations, but when it's catalyzed, it just happens faster. So there's no shift when you add a catalyst.